Hey folks, Adam Dupay here, and this is a recording for CSE 365 Fall 2019. So at this time I am traveling again, and we just released assignment 6, so it's here on the website. And so in class today, the TAs went over how to approach assignment 6, making sure that everybody understood how to get on the server, how to access all of the challenges, how to be able to get files onto and off of the server so that you can analyze them. There's a lot of really cool stuff here. I think you guys are going to be have a lot of fun here with this assignment. And so what I'm going to do today, since we did that in class, I'm going to record a lecture continuing on application security so that you can watch this and we'll get prepared for the next time. So yeah, if you have any questions on assignment 6, if you weren't able to go to the office hours, if you weren't able to go to class, feel free to please come to office hours. We'd love to get you through it. The important thing is that to incentivize people to actually finish it early, we have an extra credit option of if you finish 5 of the levels by the December 2nd, you'll get an additional 10 points on the assignment. So this will help boost your grade. And this is to really incentivize you to start early. So not all of the levels. We haven't covered everything you'll need to break all 10 levels right now. That's what we're going to be doing through with this application security part. And so, yeah, let's get into it. So as Jan kind of went off and talked about previously, so the endianness is a really important issue in binaries and understanding what's going on. So here, what we're doing is we're kind of stripping away the layers of the abstraction that we've been dealing with to try to understand, okay, what is actually going on in these binaries? And so what we're going to dig into is what does the CPU actually execute, right? So it's important to remember that processors don't actually execute what we think they do, right? We write our program in a high-level language like C or C++, but that processor, that bit of silicon, doesn't know how to execute C code. It doesn't know how to execute Python code or Ruby code or C++ code or anything. All it knows how to execute is specifically assembly code. And actually what I'll mention here is what we're going to cover here is basically like crash course, high level, what you need to know about x86 assembly to understand a binary, understand what's going on, to be able to analyze it for security vulnerabilities. But this is a really deep topic, so I'm going to say some things that aren't actually true, like the CPU executes x86 assembly code. This is actually, if you study and get into computer architecture, this is actually not true for performance reasons. Modern processors will actually translate from x86 code to a microcode that the CPU actually executes, and that gives them a lot of interesting benefits. But for right now, we'll ignore that complexity, but this is something that if it really excites you, if you really want to find out what's going on, how computers work, this is something that you can go do. So x86 assembly language, it's a slightly higher level language than machine code. So what does that mean? Well, it's important to remember that, again, just like a CPU can't execute C code, a processor needs to execute essentially ones and zeros, right? So it interprets those ones and zeros as certain instructions with data and then figures out what to do from there. So assembly language is kind of our human view of those ones and zeros that the CPU executes. And so basically, assembly language is like another type of programming language. It's just really, really close to the assembly, to the CPU and what's actually going on. So we'll see how those differ. So basically we can have directives, we can have some commands for the assembler to specify data regions that we need. We can specify actual operations, and we'll look at what are the different types of x86 assembly operations. So here is, and this is where getting familiar with hex is really important. This is a jump instruction that says jump to start executing from 08, 04, 8F, 3F. And so the CPU, when it reads that, remember, it's not reading this actual thing. This gets compiled into those ones and zeros that the CPU actually knows how to execute, but it really is a very easy mapping here. So one thing that will be very annoying is that because the assembly language is so low level, there's actually two different types of syntax of how to represent these instructions with different orderings of the operands. This may be very tricky, and as long as so the important thing to remember is every tool that you use will allow you to choose what type of assembly instruction to look at. So translating between them for automated tools is incredibly easy. So it really doesn't matter one way or the other. So AT&T syntax is the one used by object dump and the GNU assembler. And really, once you start learning this more and more, it becomes, it really doesn't matter exactly what it's in. The important thing is that's the instruction mnemonic. So in this example, it was jump, and then the source, and then the destination. So if you're going to add, you say add this register to another register and put it in the destination, which we'll see in a bit. The other type of syntax is typically called Intel syntax, and this is what's used by the Microsoft assembler, NASM, NASM, and IDA Pro. So this is actually what a lot of a lot of people actually prefer and use Intel syntax. But for this course, we're going to use AT&T syntax, and it's a little bit backwards. So the only thing that's different, so the mnemonic, the instruction mnemonics are basically the same. The difference is that the source and destination registers are flipped, so that you're actually putting the results of the calculation in the first instruction here. So again, you can change it in GDB. You can switch between these. You can, every type of, even object dump, you can specify exactly what type of output you want. So it really doesn't matter. Don't let this hang you up. I'll show you as we see some code examples, ways that you can actually just easily tell from looking at code exactly which syntax it is. So, okay, so what's the point of assembly? So essentially, as we saw, the CPU has registers which provide for fast computation right on the processor. But of course, this actually isn't enough. A modern, x86 specifically has, I don't know exactly how many registers, let's say 8, but it suffices to say there's a fixed amount of registers. So if we only use those registers, we wouldn't be able to access more than 8 times 32 bits. So that's the only amount of data we'd ever be able to compute with. Of course, we know that modern machines have way more access to way more resources than that, and that is the memory. So we need to be able to access memory, right? So that's thinking about now we're extending our model from just the CPU and accessing its registers that are literally on chip to how do we access the memory, which could be, a vast amount of memory. So to do this, so this is the specific x86 format of how we access memory. So we'll go by these step by step. So there'll be a base operation of where we're addressing. So what's the base of the memory? What's the index, the offset of that base address? So the way to think about this is in terms of an array calculation. So you have a base address of an array, and every element of the array is some index offset of the base. But different sizes of arrays. So if you're looking at an array of characters, a character is a byte, whereas let's say an array of integers, an integer is 4 bytes. So there your scale is going to be 4. Displacement is a constant offset. And so anyways, okay. So it's important to look at these as an example, I think. You can go through these and kind of... so basically what this is going to indicate is the base. So the syntax is going to be like this. So we have the base, the displacement. So surrounded by parentheses will indicate that this is a memory access. So this means this is something that talks to memory. We're either going to take something and put that in memory or take it out of memory and load it into a register. So here we have the base address, the index, the scale, and some displacement off of that. So for example, here is a move instruction that is the size of the reference. So we're moving along. So along should be 32 bits, I believe here. And we are going to do now here for the base, we can either have a fixed base, which would be a fixed memory location, or here we're using the register EAX. So we're using whatever's inside EAX. That's going to be our base. So then we just follow this formula. So we do the base, and then we're going to do plus ECX is the index here, scaling by 4. And sorry, maybe you can hear some construction happening outside the window. Sorry, it's something I can't control, so I will just keep talking over this. So we have the EAX register is the base, the index is ECX, so you can think that we're already getting some interesting things about this instruction. So again, this is AT&T syntax. Yep. So that means we're going to take from memory and put it into EDX. So we're moving along from memory, and where is that memory? Whatever's in EAX is our base. Then we're going to add to that ECX, whatever's in there, times 4. So that will give us some index off of that. And then that whole thing subtracting 20 from there, 20 hex. And we're going to move whatever's in that memory location into EDX. So again, it's important remembering memory is addressable by the byte. So we're addressing 4 bytes, we're moving those bytes into EDX. So super important thing before I go through and talk about this, actually I will look at it here. I suggest you look at these slides and based on what we just talked about, go through and think about each of these examples. Okay, what is going on here? Where is memory flowing? Is it coming, so key question is it coming from memory into a register or from a register into memory? And then what's the exact memory offset here? So here we have the base EBP, and we can see that because there's no, so we just have the base, we don't have the index or the scale, that these are essentially 0, so we can ignore them. So the syntax helps here. So we're taking EBP and we're subtracting 8 from it. We're moving from that memory location and putting it into EAX. So copy the content the memory pointed to by, and I won't say that again. Now here is a simple memory dereference, and the really important thing and one interesting thing to think about here is what does this look like in terms of the C code that would generate an instruction like this. So here and another thing to note is, do we have a problem here? We're using EAX and then we're writing to it, right? So we're fetching whatever's at the memory location represented in EAX. We're taking that memory and we're storing it back into EAX, effectively clobbering and overwriting whatever was in EAX. But that's okay. Maybe we don't need that again. So we have our register EAX that's on our chip. We're going to look at what's the address that's inside that register. That's going to point us somewhere in memory. We're going to grab 4 bytes there, and we're going to put it back into EAX. So this is exactly like C code that does a dereference. So when you do a pointer dereference, what you're doing is you're accessing what does that value of that memory that points to, where is that? So that's what this looks like. So again, remember with a move instruction, the parentheses here indicate a dereference. So we're going to go get that memory that EAX is pointing to and put it into EAX. Okay, now here we have the other way. So here we're moving whatever's inside EAX to somewhere else. And what is that somewhere else? So this instruction means take whatever's in EAX and put it in memory. What location in memory? Whatever EDX is, plus ECX times 2. So now we can see with this $sign in front, this is the syntax of a hard-coded memory address. So this is fetch whatever is at memory address 804A0E4 and put it into EBX. So this is, oh, I was wrong. Okay, this is a good thing while we're going over this. Okay, so scratch what I just said. This is actually copying the value. So this is a hard-coded value of 0804A0E4 and copying that into the EBX register. So this is how we're able to load a fixed value. This value never changes into EBX. Now the difference is, and this is where I got messed up, is the dereference occurs with the parentheses. So if we have the parentheses, then we get a dereference. So now this says so we know after this instruction executes, the value inside EBX must be 0804A0E4. But in this next line, the value inside EAX is going to be whatever is at the memory location 0804A0E4. Cool. Okay, so these are all the different ways we can access memory. Now, what do we do with that data? So we looked at how we moved information into registers and out of registers back into memory. So there's a number of different instruction classes, some of which we saw. So there's some that transfer data. So we have move, exchange, push, and pop. We'll look more closely at push and pop later, so we don't need to go into them now. We have ways of doing binary arithmetic, so we can add, subtract, multiply, divide, increment, decrement. We have logical operators to do logical ands, ors, XORs, not. We can transfer control, so this is how we get that power of programming of, for instance, if conditions, right? So, well, I think actually we will have, oh no, okay. Right, so we can have conditional jump commands, call and return. We'll see how those work later, but essentially you can think of this helps us make function calls, right? Because when we call a function, we need to know how to go back. So call gets us into a function, we can do some computation, and then we go back to whoever called us. Int and iret. Int is an interrupt, so trigger an interrupt. This is one way for this is to call system calls from our user space program into the kernel. We can compare values using the comp instruction, the CMP. And the way this is done, it's the eFlags register that we talked about earlier sets a whole bunch of flags on after a compare instruction, like a 0 flag, a CF flag, anyways, all kinds of crazy flags. And so by using different types of jump operations like JNE, jump if not equal, this checks if the compare was equal or not. JE only jumps if the previous compare was actually equal. And where to jump to can be direct, so it's a constant address like we saw, or it can be indirect. You can say jump to whatever is in the address of EAX. So this would mean you calculated that address of where to jump to dynamically. Input, output, way to talk to peripherals, all kinds of stuff. And NOP, so we have instructions that basically NOP just means no operation. Don't do anything, do nothing. Okay. So I mentioned it a bit earlier, but how do we actually invoke system calls, right? We need to be able to call into the operating system, because remember, the operating system does many, many things for us, right? As a user space program, we actually can't read and write files or do anything ourselves. We need to say, hey, operating system, please open this file for me. And we talked about why this is because we need to be able to the operating system does all kinds of permission checks, right? So we can't do it ourselves. We need the operating system to do that for us. Usually, most times that you think you're using, and also this also works for writing out to even standard out. So there's a write system call to write to a file descriptor. We write to standard out, and that's how we actually get output from the console. Usually, though, we use things like libraries. So we use the libc library that has functions like printf, which are much nicer to use than just the write functions. So, and we'll see why this is important, because as we write an x86 assembly language program, if we can't invoke a system call, we can't see the output. So we're going to actually see the output here. So here I have Linux x86. So the way to invoke a system call is by int. So the int instruction is an interrupt. And what interrupt number you're using is hex 80. And then when you do it, you need a calling convention. So how do you call a specific system call in the operating system? How do you tell it you're reading from a file descriptor, writing to a file descriptor versus any of the other 256 system calls? So what you do is you specify an EAX. EAX contains the system call number. And there's just a table you can look up for Linux or whatever operating system that says, okay, EAX is this means this system call. So we can do that. We can write a hello world x86 assembly program. In our data section, we have a label called HW. So HW colon is a label just like on C. This is how you do labels on C. So we're telling the compiler, hey, in data we have a string that is hello world /n. So very similar. Now in .text, so .text means our code segment, and we're going to tell the linker that we have a function called main that we want other people to be called. So this is how, again, how everything ties together. When you write a main function in C, it gets compiled down to this so that the operating system, specifically Linux, knows to execute this main function as the entry point. So our main function, we'll walk through this. So we'll see what's going on here. So we're going to move 4 into EAX. So again, okay, so important things here. First thing, the $ means a constant value, so we saw that. So move L $4 into EAX means move the constant value 4 into EAX. Now, as I told you before, there's a cheat to understand exactly what the syntax is, right? So the difference between, one of the key differences between Intel and AT&T syntax is the order of operations. So if you had no idea what types of syntax it was here, looking at this instruction actually tells you exactly everything you need to know, at least in terms of where the destination operand is. So how do you move? So there's only two possibilities. Either we're moving 4, the constant value 4, into the register EAX, or we're moving whatever is inside the register EAX into the constant value 4. Now, we know that this move operation is not in parentheses, so this is not a dereference, so there is no 4. There's no way we can move EAX into 4. That's essentially a meaningless operation. We can only move the constant value 4 into EAX. So we know that the destination register must be the last one, which is AT&T syntax. Okay, so that aside, we move 4 into EAX, we move 1 into EBX, we move the address of, so now this is some nice thing that why we're not coding directly in machine code is that the compiler will be able to substitute in the address of HW wherever it puts this string in memory. It will put that address here and say, okay, move that value into ECX, and then move the constant value 12 into EDX, then call int 80. So, whoa, what instruction is this being executed? So let's figure this out. Let's look up x86 Linux syscall table. Okay, so there's great resources on the web. I did not preload this, so I have no idea if this will work. 32-bit says it's coming soon. That doesn't seem promising. So let's look at this. Linux system call table. This is for the Linux 2.2 kernel. We want to make sure we're in the right place. This number will be put into the register EAX. Great. Okay, so we put 4 into EAX, which means that it is a write system call. How do I know what the parameters are to the write system call? I can do man to write. So section 2 is specifically syscalls. So here I can read this. I can say write to a file descriptor. What's the arguments to this function write? File descriptor, a pointer to a buffer, and count. So what's the description? Write writes up to count bytes from the buffer starting at buff to the file referred to by the file descriptor FD. Great. All right. So we know we're putting, okay, so we know we're calling write. So this means an EBX is the first argument, which is the file descriptor. In ECX is the buffer that we're writing to. And in EDX is the size. So we can now go back to here. Actually, let's just go here. So we can now go back here, look at this, and we can see, okay, moving 4 into EAX. So we are calling the write system call, WRITE. Then we're moving 1 into EBX. So this means that we're writing to file descriptor 1. What is file descriptor 1? Again, it's really important to remember your file descriptors. This is something that is got to be kind of in your core. So 0 is standard input, so reading things from the user is file descriptor 0. File descriptor 1 is standard output, so this is for you outputting, and file descriptor 2 is standard error. So this is where you usually print error messages. Okay, so we move that into EBX, so we're going to write out to standard output, and where's the buffer that we're going to write out? So it's at the address HW. So this will be a pointer to this string. That'll be HELLO space WORLD. Then the question then is the last parameter was how many bytes are we writing out? So that's the count. So the count is 12. So this will do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it'll do everything. Hello space world and a new line. And that'll happen after we do the int 80. Then what happens afterwards? So the system call returns. We can see that it returns some size value. What's the return value on success? The number of bytes written is returned. It's returned in the EAX register, but let's ignore that. We don't really care. Then here, then we're moving 0 into EAX and returning. So we're returning 0 from this function, which is essentially main. So what does this look like? Let's write this up and see what happens. All right. And I'm going to call this hello-s, so capital S is assembly. Now you should be able to just do GCC, tell it to compile hello.s. I'm going to do -m32. And of course, I didn't try this out in advance before making this video, so I apologize for that. Let's see. Wonder if this will work. No. Man, NASM. Let's go AT. Trying to look for syntax. Yeah, I don't think that's going to work. Okay, the problem is the loader, so I just need to compile x86 on 64-bit Linux Ubuntu. So the problem is I don't have the right libraries to compile 32-bit apps. There's some, there we go, multilib. So this should install glibc for all of the things, although I guess maybe for the loader. Yeah, it needs glibc to load it. Okay. So let's see, it's installing. Just like in class, I'm not going to pause the lecture. All right, let's see. There we go. All right, well, we don't know that it actually worked. Let's run it. We see that it says hello world with a new line. Great. So now let's look at what actually happened. So now I'm going to open this up in GDB. I'm going to I'm going to first examine the instructions at main so we can see. So move, the syntax changed. So yeah, let me set disassembly flavor. So you can see I sometimes use this. So now it changed it. See, I told you it was very easy to switch back and forth. So we can now look at our instructions and we can compare this to what we had here, right? So here we have our main function is move 4 into EAX, 1 into EBP, move 2008 into ECX, C, which is 12, into EDX, int 80, move 0 into EAX, return. And now, so the key difference is this value. So we should be able to examine, and so here we're asking 2008. So here we're asking GDB, hey, examine what's at this memory location, 2008, and print it out and interpret it as a string. So here we have the string hello world new line. So the compiler decided to put it there, and then it substituted this in for here, and so that's why everything works. And so, yeah, we can let's take it for a quick spin and show you a bit of the disassembly. So we can break on main, restart it. I'll actually be talking about this environment. This is the GEF version of GDB, which is very, very useful for doing things like what we're doing here. Because I can see we're at this instruction here. We're about to move 4 into EAX. I can look at all of the registers that I currently have. I can say next instruction. So we just move that there. So 4 is into EAX. I can do, let's do step instruction. So 1 is now in EBX. And okay, a question would be, why is this value not exactly what we saw, the 2008? The reason is address space layout randomization. So there's a lot of, so basically when Linux loads our program, it shows a random memory location to load it into. So that's why it wasn't exactly the same, but that's okay. Into ECX, and we can see here GEF does something cool, is it shows me that, oh, hey, so 4 doesn't point to anything. There's nothing at memory address 4. There's nothing at memory address 1. But at this memory location, that is a pointer to the string hello world. So it's actually able to do this interpretation and figure out roughly what things are. So step instruction, I can say move C into EDX, and it's about to call an int 80. So I know right now it's going to call system call 4 EBX to, so it's going to write to file descriptor 1 with the string hello world and 12 characters. I can do one more, and I can see that it output that, and I can see that actually the return value changed to be 12 because that's how much it output. It's going to move 0 into EAX. We're going to return and go, and then exit. So there we go. That was our hello world. Okay, but what actually happened, right? So we had our program executed. So, and if we look here, right, so we kind of have this insane thing that happens. We compiled our hello.s, so we compiled the assembly language, and what it did is it produced a file, a.out, that is an ELF 32-bit executable that runs. So, and this is, again, breaking down. So we looked at, okay, so we have C code that gets compiled down to assembly code, which is what the CPU actually executes. But how does that program? So remember, it's kind of an interesting thing to think about. A C file is just a file, right? It's just a collection of bytes. So you have your compiler that translates that to an executable file in assembly, but that again is just a file on the computer. And I can see here, if I do ls-la, I'm looking at just files here. I have hello.s and a.out. So a really interesting question is then, how does your operating system take that file, this a.out, and actually turn it into a running process? So this is where that ELF file format comes in. So the ELF file format describes, basically, one of the things it describes is an executable binary. So here I have, and that's when I ran file a.out. I can see it's an ELF file. And so essentially, the operating system needs to be able to take a file on disk that represents a program and turn it into a running process. So, and this is the basic idea. So the operating system needs to, and this happens through the exec-ve system call, but we'll get into that later. But when a program is invoked, so when we run ./a.out, our shell is actually asking the operating system, hey, please execute this program. So what does it do? Well, it parses that ELF file using all the file formats. It copies parts into memory, and you can actually look at, let's go back here. So on Linux, the /proc file system, which if you're trying this out on our shared server will not show you anything because I've disabled it, I believe. So proc self, so self is your process. So if I run cat, so I can see the memory layout of cat. So I can look at all all of this, I can see where all the regions are laid out into cat's memory space. So it figures out where to copy everything. So remember, the code needs to go somewhere, the data needs to go somewhere. If, as we saw in that example, if there are references that need to be changed based on where it's laid out, so this relocation happens. And then finally, the instruction pointer is set to the location that the elf header specifies as part of the address. Then execution begins, and then it starts executing, and then at this point, and it's important to remember, and this is kind of the key to assembly language, is that CPU is very dumb. All it does is start executing wherever the program counter says it should, the instruction pointer, fetches that instruction, decodes it, figures out what it's supposed to do, and then goes to the next one and keeps executing. And then if there's a jump, it will jump and go somewhere else in memory to execute more things. So on x86, so processes think they have up to 32 gigabytes of memory. So this is a representation of the process memory layout for specifically 32-bit systems running 32-bit applications. So it's just an interesting performance benefit here that the kernel used and took up the first 1 gigabyte of memory, but we can ignore that for now. But typically, if you're on a 32-bit system and you're running a program, memory starts at a high end, which is BFFFFF, and has all the way to 0 at the end. So a program effectively had about 3 gigabytes of memory. So you can see why the jump to 60. So, and again, if you think about why were we limited to 4 gigabytes, it's because addresses and pointers could really only access 2 to the 32 bytes of memory, which is 4 gigabytes. And you can see one of the big benefits of moving to 64-bit processors is the fact that we can access 2 to the 64 bits of memory, which is a lot. So then what does this process look like when we actually start digging into it? So we need everything that gets passed to our program. So our program executes, and if we look at the main method, we have the main method, we actually have, so when we write like a typical C program, we have our main method where we take an argc, so the number of arguments, argv, and actually you can take in another argument, which is the environment pointer. So all the environment variables that gets passed into your program. So all of that actually lives above. So at the very top of your memory is your environment, your argument variables, which include environmental data and command line data. So all of the actual data is passed there. Then these arguments are passed. So we'll dig into this. Then we have the part of memory that's known as the stack. So essentially, it really comes down to to function calls. So you have one function that calls another function, then you call a third function, which calls a fourth function. If you think about that, all of those functions need to use the registers that are on the processor, right? And specifically, when one function calls another function, it wants it to return at exactly the same location, exactly the same state that it was in, besides whatever computation that function provided. However, how can we do this if we only have a fixed number of registers, right? So if we have a fixed number of registers, how do we get it such that we can have, function calls that are 100 deep that literally are longer than as many processors as we have? So what the idea that came up with this was essentially a stack in terms of the data structure, and we'll look into this, but basically you can think of it right now as the stack is the location of memory that starts at high memory and grows down. Then we have our shared libraries, so any like libc or other libraries that we're using get loaded into the shared library. Then so the stack grows downwards, but and those of you who did the secure house in C++, or if you remember reading those examples in C++ code, those folks were able to read in as much memory as much data as possible. So oftentimes our programs don't know how much data they're going to get in advance, right? There's actually pretty fundamental concept and notion inside of computing is you don't know the size of the input that the user is going to give. The user can give arbitrarily large input, so there's no possible way for you to allocate enough memory in advance. So what do? You need some mechanism to be able to dynamically allocate memory. And so that is in C or C++, you can use so in C you use malloc and free. In C++ you use new and delete. Similar concepts exist in Java, but we'll ignore them now. And so you need another place in memory that grows depending on how much data you're using. So that's what we call the heap. And if you think about it, there's this really nice symmetry. So you have this stack that grows as you do more and more function calls, right? So you need some part of memory that grows and grows and shrinks, right? So it grows and shrinks and grows and shrinks. Similarly, we need some type of memory location that also grows and shrinks based on how much data that we're using. And so what we do is we situate these against each other so that each of them can grow towards the other. Finally, we have a section that has all of our global and static variables. So whenever you have a global variable, it's in the either BSS or data section. And finally, we have our code section, which is towards the end here. And specifically, so the code section is usually marked as read-only so that you can't modify and change the code at runtime, although you can get around that a bit. Okay, cool. So now that we've dug in a little bit, we need to kind of step and think about how do we go about analyzing these programs. So I showed you a little bit here. So we need to be able to, so specifically in terms of security, we've been operating a lot of times on source code, but you may not have source code. In fact, you may just have this a.out binary. So the question is, how do you know what it actually does? And so this key thing is, again, remember if we just did a hex dump of a.out, this hex dump is, so this is an ELF file, so the ELF file has some metadata, but eventually it's going to get into, here's just some code that the CPU executes. So how do we actually make sense of that? So we can use different tools. So this is object dump, which tries to disassemble everything. And if I look for main, so here's my main. And so I can see, so object dump says, these bytes B804000000 are actually interpreted as an x86 instruction of move constant 4 into EAX. BB01000000 is move 1 into EBX. Cool. So how do they actually work? So disassembly, so we looked at compilation and how compilation is how C gets compiled into x86 assembly, and then x86 assembly is compiled into those bytes. So we need a way to go backwards. So that's the process of disassembling. So disassembling gets you from basically like raw bytes into what is the binary so what is the assembly language representation. So there are a lot of tools. I'm going to go over many of them here. You can kind of explore them on your own as you tackle these challenges. So Radaware is a program analysis tool. You can go check it out there. It has reversing and vulnerability analysis. You can disassemble binaries. It has a lot of scripting capabilities, which is really cool, and people use it to automate disassembly of binaries. It's free, which is cool. IDA Pro is the state-of-the-art tool for reverse engineering, although that's changing a little bit. So you can go to this website, you can check out IDA Pro. It supports disassembling of binary program. It also supports decompilation. So decompilation is that next step, right? So you have your C code, you take your C code, you compile it to assembly, which gets essentially assembled down into the binary code. And so disassembly is taking binary code into assembly language. And then, but what would be really nice is not operating on assembly language, operating on C code. So decompilation is the process of how do you smartly go from that assembly code to C code. So IDA Pro has currently, I think, one of the best decompilers available in the Hexraise decompiler. It is very expensive in terms of this Hexraise decompiler. It costs about, I think, $5,000 to $10,000 per architecture or something crazy like that. Although I'll say this for those of you who really want to get into security. As of now, IDA Pro is like the de facto standard tool that everyone uses. But there is a version that's available for free that's, I think, a few versions behind, so you can actually check it out on your own. Other tools, Hopper is a tool that I use that's kind of native to Mac. So it has a decompiler actually in it. It's kind of crappy, but it sort of works. It's pretty good. It's only it can be used for free with a time limit, and it's on the order of IDA. It's around $90, which I wouldn't recommend unless you're really trying to get into this area. The other thing that came out recently is Ghidra. So Ghidra is actually an open source reverse engineering suite from the NSA. So this happened a year or so ago, where the NSA released their internal reverse engineering suite of tools called Ghidra, Ghidra. So you can go there, check it out. It's actually very interesting and cool to see the NSA contribute back to the community. And of all these tools, it's the only open source tool, except for, Rodaware is open source, I believe. But I'm not 100% certain. But anyways, Ghidra is very cool. This is actually, so the interesting thing is Ghidra is putting a lot of pressure on IDA Pro. So IDA Pro's been, so if you can, IDA Pro has, so with all these tools, you have the ability to add comments and rename variables in the binary code, so you can kind of get more semantic meaning about what's going on. For the longest time, it was crazy because IDA Pro didn't have an undo button. So if you think about trying to write code in like early versions of Notepad, which only allowed you to undo once, think about undoing 0 times. So yeah, it was a thing that people complained about a lot. IDA Pro never fixed until magically when Ghidra was released, it has the ability to undo. And so now IDA Pro also has that ability. But I don't want you to get super hyper focused on these tools. I think if you're really into this, you can definitely use the tools. And I want to make 100% clear, you do not need to use one of these tools in order to do this assignment. And actually I think it's preferable to start with low technology tools so you understand what's going on. So the actual tool I recommend you start with is Object Dump. So that's what you saw me just use in the command line. Object Dump is the standard. It's a GNU development tool. It's a linear disassembler, just tries to disassemble bytes into instructions. And it's just do object dump -D means try to disassemble everything, the binary, and then give it a binary and then pass it through less is the idea. So this is one of the, it's like so that's what we're looking at here is just the output. It's nothing fancy. It doesn't give you any fancy output, but really, being able to understand what's going on at this level is super important. But to understanding what's going on, so disassembly is important for trying to understand what's going on from the binary level, because you need to understand the code to see what's going on. But you can think of that as a static technique. So you don't even need to be able to run the binary. As long as you can look at that binary, analyze it, and understand what it does, maybe you could find vulnerabilities in it. The other way to tackle binaries and try to understand what's going on and try to identify bugs is debugging. So actually try to debug the program at runtime to try to understand what it's doing. So I think debugging is a super important skill that will benefit you beyond this course. So in your other courses, So, going beyond using print statements for debugging and using an actual debugger, and I will say print statements can be great and can really help you in figuring out what's going on. But sometimes, and especially for low-level things like this, being able to really dig in to be able to understand what is going on in this binary is a superpower that will set you above your peers on the job market, in your jobs, everything. What you're really doing, and you don't need source code to be able to debug. That's really interesting. I have stories of folks who are so good at debugging and reverse engineering, they actually debug and find bugs in like the windows that cause their computer to slow down. So you do not need source code to debug a program, and you'll debug it exactly at the assembly language level. And you get runtime introspection of what the program is doing, which is super important to reverse engineering. So you can think of disassembling as looking at the binary code statically to understand what it's doing, whereas debugging is analyzing runtime behavior to see what's going on. So one of the easiest and best tools, actually GDB I use all the time for debugging, it's the GNU debugger. You can analyze if you've ever had a program crash and it creates a core dump, a .core file. You can actually debug it, analyze the memory, look from there. You can start a program for debugging, which I did earlier, or you can attach to a running process. Super important, and the documentation. So GDB, I will say, has a pretty difficult learning curve. It's hard to get started, but I guarantee you that if you put effort into learning how to debug with GDB, it will save you way more time in the long run. And it has a really good documentation. So you can set breakpoints to halt your program. You can set breakpoints on certain conditions. You can examine the memory, stack layout, everything. It's an incredibly powerful tool. And even better is you can script your debugging. So you can set commands to execute when a breakpoint is hit. So you can do things like, when this instruction executes, print out the value at this memory location. It is incredibly useful. Like I find many instances where I need to do this. I believe Facebook had a post a long while ago about using the poor man's debugger, a poor man's logging or profiling to see what code is executing often, and it used GDB scripting for this. So it's insanely powerful. You can change things at runtime. You can do all kinds of cool stuff. You can also extend GDB. There's basically, as I understand it, there's a couple different kind of extensions to GDB that folks use. So one was the GEF that you saw me use that I actually really enjoy using. Pwn DBG is another one. There's a whole bunch of other ones, and the idea is they turn the basic kind of GDB experience into something slightly better, like we saw, so which gives you much more information. Excuse me. I will say you do need to take your time, understand this, so understand, you're typing in commands into here, this is a stack layout, all your registers, all this kind of stuff. So here, this isn't, so to not freak you out, this is a x86-64 program. So we can see the different registers here are not the EAX, EBX that we've been looking at. Okay, cool. So that's the crash course in what's going on. Now, what we're going to be doing is we're going to be looking at how do we think about attacking a Unix system. So this is, very timely advice since you just got a homework assignment that is explicitly attacking Unix systems. So when we think about it, so conceptually, and this is what hopefully Jan talked about in the beginning part of this program, so of this section, so in the last lecture. So thinking about, okay, here's a system. How do I exploit it? Or how do I trigger a vulnerability or make it do something fundamentally that it's not supposed to do, right? So conceptually, thinking about this. So here's this system. Well, one option would be, what if I just change the code? I change the code and I can let it do what I want, right? Well, it's like, well, that's kind of cheating. Like, what if you can change the code, you already can make it do anything. So that's just either a crazy bug and that's really bad, or it's not really something you should expect to have happen, right? So if I want to influence the behavior of this system and I can't change the code, what can I change? Right? The important thing to remember is the only thing that you have control over is the data that flows into that system. And so thinking about, okay, where are we in relation to this system? So if we have some remote server somewhere, then maybe the only thing we can do is attack network services that are on that machine. So this ties in when we talked to networks, we talked about network security, we talked about the importance of reconnaissance, right? Being able to understand what applications are running on a remote system gives us targets of, okay, now I know I need to find a vulnerability in one of those remote services in order to get access to that machine. We can also try remote attacks against the operating system. So this is bugs at the TCP/IP stack level. We maybe can do remote attacks against a browser. This is how a lot of compromises, actually real-world compromises, happen against companies. So essentially what they'll do is, so they'll figure out who are employees of the company through something like LinkedIn. Then they'll figure out who those people's friends are on Facebook, so they'll try to, of course, break into Facebook accounts or something of those people. If they can't do that, they will try to break into your friends' Facebook's accounts, then send you a link on Facebook Messenger to say, hey, go look at this thing. Then when you click on that link, they use an exploit against your browser to get access now on your computer. And of course, you're on Facebook during work hours, so it's on your work computer. And now they have access to you. They have a foothold into the organization, and they'll propagate from there. Other ways of targeting Unix systems. So we know, local and remote here. So remote, we do not have access to the system. We cannot run commands. But if we're local users, that means we have a user account on the system. We can run commands as that user, as our user, right? So we have permissions of what we can do. But we want to escalate our privileges. We want more, right? We want to be able to get root access on the system. So what's our target there is targeting specifically setuid applications. We could also try local attacks against the operating system, because if that's successful, then we're able to execute with the permissions of the operating system. So, of course, here we're going to focus on specifically local attacks. So when we're attacking Unix applications, basically 99% of local vulnerabilities exploit setuid root programs to get root privileges. Very little of them target the operating system kernel itself. If you think about why this is, it kind of makes sense. The operating system kernel gets hardened as more and more people find bugs in them, because any bug in a Linux kernel is likely applicable to almost all Linux systems, and therefore you need to target different types of vulnerabilities. So the question is, what things influence the running of our application? So again, thinking about what of our data that we as attackers control, how does that influence the application? So that can be based on inputs, which could be, so what kind of inputs get into a program, right? It could be the command line arguments. We know the command line arguments get passed in as part of argv. So in any application, our arguments come from the attacker. Also the environment. So all of the environment variables, and the environment could be pretty large here, right? It could be, so here we're thinking specifically, environment variables. So the environment that the program executes in influences its operation. Then things that happen during execution. So for instance, dynamic linking of objects, file input, socket input, all of these things are inputs from us that we can potentially control. Then, again, as we saw, applications do not execute in isolation, right? They need to be able to interact with various things, for instance, the file system, right? So, but if we're running a setuid application, we control at least part of the file system, right? We control everything that we have access to. If we, we can't just change things that are owned by root that we don't have permissions over. This is why we went over the Unix permission model so much. We can create other processes. We can invoke other commands, signaling. So sometimes defining exactly what constitutes the boundaries of an application is incredibly important. So or is, sorry, not just important, but it's very difficult. It's like, what is the actual input? So if you think of, you can think about some systems, maybe you can't get input, but you see, oh, they're actually using tweets that tweet some hashtag out. Well, that's a way that you can get input into that application. Maybe it's possible to trigger a vulnerability that way. All right, cool. So I think we have made actually fantastic progress here, probably because I didn't have, and we maybe went a little fast. This was a pretty dense lecture, but I think we have a really good kind of starting off point here. Yeah, so what I'm going to do is I will stop here and we will pick back up on attack classes, and we'll go. And so next class will be super cool. We're going to start going through really interesting. So we're going to go through all the things that are in dark here. So path attacks, command injection, and stack corruption. So we're going to really dig into the fundamentals of how computers work and see how we can subvert them for the attacker's benefit. So thanks for watching, and I will hopefully see you next time.